You ever look at a massive bridge or the graphics in a video game and wonder, how does that work? Well, it all comes down to this hidden language of shapes and lines. And today, we're going to make you fluent. So, here's our game plan. We're going to build the ultimate geometry toolkit together. We'll start with the real basics, the alphabet of geometry. Then we'll dive into triangles and their unbreakable rules. After that, we'll check out a cool copy-paste tool called Similarity, explore some of a triangle's secret centers, and finally, wrap it all up into a problem-solving toolkit you can use anywhere. You guessed it, the answer is geometry. They're all built on this fundamental visual language. Think of it like a secret code that tells us how shapes and structures actually work. And right now, we're going to unlock that code together. All right, first things first, we have to learn the alphabet of geometry. These are the super simple, but honestly incredibly powerful rules that tell us exactly how lines and angles behave when they meet. Okay, so this might look a little complicated at first glance, but trust me, the idea behind it is super simple. See how you've got that one line cutting across two parallel lines? Well, when that happens, it creates this totally predictable set of relationships. For example, look at the angle in the top left. Now look at the one in the bottom left, in the same position. Those are called corresponding angles, and they are always equal. The same thing goes for vertically opposite angles and alternate angles. Once you get this, you've basically got a master key for solving a ton of geometry problems. Okay, so we've got our alphabet down. Now let's start building our first word, or in this case, our first shape. And honestly, it's probably the most important shape in all of geometry, the triangle. And this little shape, it follows three simple but totally unbreakable laws. So here it is, property number 1. And this is probably the most famous rule in the book. The three angles inside any triangle, I don't care if it's tall and skinny, short and fat, or a perfect right angle, they will always add up to exactly 180 degrees. No exceptions. It's a game changer because it means if you know two of the angles, you can always figure out the third. Okay, rule number 2 is just brilliant. It creates this direct connection between a triangle's sides and its angles. It's super intuitive, too. The biggest angle is always staring directly at the longest side. And the smallest angle? Yup, it's always opposite the shortest side. So you can just glance at a triangle and without measuring anything, get a really good idea of which side is the longest just by finding the biggest angle. And for our third unbreakable law, we have something called the triangle inequality theorem. This is basically the gatekeeper rule. It decides if a triangle can even exist in the first place. Here's the deal. If you take any two sides of a triangle, their combined length has to be longer than the third side. If it's not, well, you physically can't connect them to make a corner. They just won't reach. All right, so we've got the rules for a single triangle down pat. But what happens when you have two triangles? How do we compare them? Well, that brings us to our next big idea, what I like to call the copy-paste tool of geometry, similarity. So let's get this straight because it's really important. You've got two main ways to compare triangles. First, there's congruence. Think of congruent triangles as identical twins. Every angle, every side, they're exact copies. Then you have similarity. This is more like a photo and its enlargement. The shape is exactly the same. All the angles match up, but one is just a scaled up or scaled down version of the other. And you can see that difference perfectly right here. Up top, in case 1, check it out. The angles are identical, but the sides are clearly different lengths. That means they're similar. Now look at the bottom, in case 2. Everything lines up. The sides are the same, the angles are the same, they are perfect copies. They're congruent. Now here's where the magic of similarity really kicks in. Because the triangles are just scaled versions of each other, the ratio between their matching sides is always the same. What does that mean for you? Well, it means if you know all the sides of one triangle and just one side of a similar triangle, you can figure out all the other missing sides. It's an incredibly powerful shortcut. Okay, but here's where it gets really interesting and a little tricky. When you look at the area of similar triangles, the relationship isn't what you'd expect. It's not based on the ratio of the sides, it's based on the square of that ratio. So if one side is twice as long as its counterpart, the area won't be twice as big, it'll be 4 times as big. It's a massive shortcut, but it's one that definitely catches people off guard. All right, we've pretty much mastered the outside of the triangle. Now it's time to go inside. Every triangle has these 4 secret power centers hidden within it, each one with its own unique properties. Let's go find them. Yeah, you can really think of these as the triangle's command centers. each one is found in a totally different way, and each one tells us something special about the triangle's geometry and its sense of balance. First up, we've got the incenter. So how do you find it? Simple. You just take each of the three angles and slice them perfectly in half. Where those three lines meet, that's your incenter. And what's so special about it? It's the one and only point inside that triangle that is the exact same distance from all three sides. Pretty cool, right? It's so perfect you can draw a circle centered there that just kisses the inside of each side. Next, we have the circumcenter. Now for this one, we ignore the angles and focus on the sides. You find the exact midpoint of each side and then draw a line that's perpendicular, at a perfect 90-degree angle. Where those lines cross is the circumcenter. And remember how the incenter was equally distant from the sides? Well, the circumcenter is equally distant from the three corners, or vertices. This makes it the perfect center for a circle that goes around the triangle, hitting all 3 points. Okay, number 3 is the orthocenter. The name sounds a little intense, but the idea is actually just about height. And altitude is just a fancy word for a line you draw from a corner straight down to the opposite side so it forms a right angle. Where those three altitudes meet, that's your orthocenter. And this one's a bit of a wild card. As you're about to see, its location can get a little crazy. And last but not least, we have the centroid. This is, for all intents and purposes, the triangle's center of gravity. If you were to cut the triangle out of a piece of cardboard, this is the exact point where you could balance it on your fingertip. You find it by drawing a line from each corner to the midpoint of the opposite side. And what's really useful is that the centroid always cuts each of those lines, called medians, into a perfect 2-to-1 ratio, every single time. And this is where it all comes together so beautifully. Look at this. For a normal acute triangle, all 4 of those centers are tucked neatly inside. But then, look what happens with a right triangle. Bam! They scatter out onto the edges. And for an obtuse triangle, it gets even weirder. The circumcenter and our wildcard orthocenter actually jump completely outside the triangle. It's just an amazing visual that shows you how a triangle's very identity is shaped by these hidden centers. Okay, let's take a breath and bring this all together. We've gone all the way from simple lines and angles to the secret centers deep inside a triangle. And along the way, we've built ourselves a seriously powerful problem-solving toolkit. So here it is, your new toolkit. You've got the rules for parallel lines, the 3 unbreakable laws of triangles, you understand congruence and similarity, you know about the 4 special centers, and you've got that tricky area-side-square relationship. But look, the real magic isn't just knowing these tools exist. Mastery comes from knowing which tool to pull out at the right time to take apart and solve any problem that gets thrown your way. So now you've got the toolkit, and with it, you've got the code. From the architecture of a building to the design on your screen, you can now see the hidden geometry that shapes our entire world. So the only question left is, what are you going to analyze first?